Today we're looking at rational functions. We're going to start super simple so we can watch what happens, and then we'll unveil it into a general strategy. So a rational function, rational basically means fraction, and a function obviously is, we've talked about functions, they have an input and an output. And the reason why something would be a rational function is mostly because the x would be in the denominator. So you have x's in a denominator. Before we had polynomial functions were more like x squared, x cubed, x squared, x like that. Now it's like we basically have two polynomial functions on top of each other. So it's kind of like we have p of x over q of x, where p of x and q of x are polynomial functions. That's why it's in this unit. So that's what a rational function is. Now, our main concern here is going to be sketching these rational functions, and our main goal is to identify ways to generalize that sketching process. Like, what are sort of the key elements? Like when we did polynomials, things that were really important for polynomials were zeros. That's still going to be important for us here. Whoops. The sort of max or min was important. In some cases, the end behavior was important. That's going to be important here as well, and so on, right? Like we had all these things that we paid attention to for polynomial functions. And one of those, like with end behavior, we went as x gets really big, what happens? As x gets really small, what happens? Okay, what happens at the zeros? Where is it positive and negative? But the one difference was that polynomial functions, if we think of the domain, it was always all real numbers. The range, sometimes depending on if it was an even or odd, would be different, but our domain was always all real numbers for polynomial functions, which means we could have put any x in and we would have gotten a value out. And this is really important because for rational functions, you start getting a problem with the domain, right? Because the domain is what you can put into this function as x. So if we start making a table with x and f of x for our simplest case of a rational function, which is 1 over x, that's your base case, just like for a parabola, x squared is your base case, like your general form. If we start plugging numbers in, we can put a lot of numbers in. We can put a 1 in, a 2 in, a 3 in, a 5, a million, negative a million, negative 2.75, but there's one number we can't put in, and that's because we can't make the denominator 0, right? So there is one problem number, x cannot be 0. So that affects our domain. So let's see how that affects our graph. So let's just start plugging in points. So if we had a 1, then you'd have 1 over 1, which is 1. So 1 is a point, okay? 2, that'd be 1 over 2, which is 1/2. So at 2, it's a half. At 3, it's a third. At 4, it's a quarter. At 5, it's a fifth. At 6, it's a sixth. I can't draw this that small, but I'm just in your mind, imagine at 7, it's a seventh, and so on. So what happens? Is it ever going to cross that 0 line this way, if we're going this way, right? At 8, it's going to be 1/8. At 10, it's going to be 1/10. At a million, it's going to be 1/1,000,000th, right? So no, it's not going to ever cross. And so what happens with that, you end up getting an asymptote. That's a line of convergence, but not passing. So like it will never pass this line, but it will get super, super, super close. So as x goes to infinity, just like in the past, we thought what happens with end behavior, you can think, okay, what happens when I put 10,000 in? Well, it's going to be 1/10,000th. So it's getting closer and closer to 0. And sometimes you can say 0 from the right if you put a little plus sign. It's approaching 0 from the positive side, not from the negative side. You can write 0 as well. So the asymptote equation is y equals 0, right? Because it's approaching that line. So that's one asymptote. And with rational functions, asymptotes are basically the most important thing because they kind of constrain where our graph can go, right? Okay, so we've gone from 1 up, but that means we haven't graphed anything for less than 1, so we have to go there now. So let's start looking like this way, right? So what if I had 1/2? Well, 1/2 would be 1 over 1/2, which would be 1 times the reciprocal, so that would be 2, right? 1 divided by 1/2 is 1 times 2 over 1, which is 2. So 1/2 becomes 2, 1/3 becomes 3, 1/4 becomes 4, 1/5 becomes a fifth or 5, 1/6 becomes 6. And again, do you think we have another asymptote here? Yes, we do. And this one's a little different, right? And that asymptote is actually occurring because if I say 0, that will not exist. But if I say 0.000007 or whatever that is, that's going to be 1 over that really small number, which will actually be a big number. So as x approaches 0, we're getting f of x goes really big to the infinity. And well, that's from the positive. Now let's look on the other side of that, right? Because we still have not explored what happens for negative x's. So imagine when we put negative x's on all of negative for all of these inputs, what's that going to do? Well, all of my answers will be the same as the black answers, but they're just going to be negative, right? So -1 is going to give me -1. That's not probably the most useful, like knowing that 1, 1 and -1, -1. Those are like the nicest points to make sure you definitely have correctly. And then everything else, -1/4 is going to be 4, right? Like -1/5 is going to be -5, and so on. So on this side, as x approaches 0 from the negative, f of x gets really, really negative. And the other way again, and you can imagine -2, 1 over -2 is -1/2. And just like we did, all of those same points are going to happen. And I'm just going to draw it in black because it's all part of the same function. Just weird looking at the negative. So that black line, and we'll emphasize it maybe in purple, that is our graph of 1 over x. But the important piece here is to consider what the asymptotes were. So we had an asymptote at y equals 0. That was here. And it panned out that it also worked on the negative side as well, because as x went to negative infinity, f of x went to 0 from the negatives, right? And this is all based on points, right? Like, what were the points? Like, you're just throwing points in and examining what's going to happen. But we can start making generalizations so that we don't always have to do it through points. We can start assuming the graph is going to be like a cobweb around the asymptotes. Because as these get more complicated, the really important thing is what are the asymptotes? Because it'll kind of like curve within those. So the other asymptote, what is the other asymptote here? There's not just y equals 0, but there's one more asymptote. Does anyone know what the equation of that other asymptote is? So y equals 0 is the flat line. What's the other asymptote? So this y equals 0 asymptote comes from end behavior, which means that it could be crossed in the center, but it does not cross that line. As it converges to that line, it becomes closer and closer to that line. The other asymptote that we have comes from a domain restriction. Because since x is not equal 0, then there is an asymptote at x equals 0. That's my second asymptote. You can see that here. X equals 0 is this line. I have two asymptotes. One that comes from the domain, and one that comes from end behavior. And so the one that comes from end behavior is you looking at, what if I plug a really, really big number in for x? Or what if I plug a really, really negative number for x? Where does it converge to? So that's one kind of asymptote. The other kind of asymptote is going to be a vertical asymptote. And vertical asymptotes come from domain restrictions. Because we can't just like have the graph going straight and then having just nothing at 0. That's called a hole, and I'll address holes later. But at this point, what happens at 0 is what's around it ends up actually getting really big or really small beside it. It doesn't just like run into 0 and stop at 0 and then keep going. It kind of like, it creates this blockade because 1/2 is 2, 1/3 is 3, 1/4 is 4, 1/5 is 5, and so on. 1/1,000,000th is 1,000,000, but it still never gets to 0. Like it gets really big, but it doesn't touch 0. So, I mean, we can go on to Desmos and type that in and see, like, explore it as something that we zoom in on. And this is really just doing all of that, calculation for you. Here's our graph. We have our asymptotes that it's getting close to. You can literally just keep scrolling and looking at what's happening super big, right? And it just keeps getting closer and closer, and it'll never really quite touch, because at 63, it's 0.00 or 0, it's 1/63, and so on. And you can just imagine it just does that for big numbers. But then you can also go this way, and it's just gonna get closer and closer. It'll never cross, never touch, right? So in your mind, you can see this, but you know, like, you're not gonna be able to graph that completely. You're just gonna graph the basics like this, kind of what the basic shape looks like. Okay. So let's try something that has different asymptotes. Well, maybe you'll start seeing the pattern as we move. So here's another example. So this one is not 1/x, it's 1/x plus 2. So we get our vertical asymptotes from domain issues for the most part. This is just like, unless something crosses out, that's when we get a hole, but nothing's crossing out here. We'll talk about that later. Vertical asymptote really is paying attention to what does not exist for my x, and that's going to be basically my vertical asymptote. And my other asymptotes, which are usually referred to as horizontal asymptotes, this comes from end behavior. It looks from you looking at the extremes. So think in your mind if you can identify a vertical asymptote and like a end behavior asymptote. We can't put a -2 in, right? Yeah. So because we can't put a -2 in, right, x cannot be -2. That, unless there was some sort of simplification that happened, this directly will imply that x equals 2, -2 is an asymptote, meaning that x equals -2 is going to have a point where, you know, because this is positive, I can plug some numbers in and confirm it's going to be going like that and going like that at those places. So I'm just pinning down what I know so far, but I'm pretty sure that basically, I mean, you can think of this also as a shift, right? If I had 1 over x, I knew that was just your basic shape like that. If I'm shifting it, replacing the x with an x plus 2, that means it's going to shift left 2. That's another way of thinking of it, is essentially we're going to have, like if we think of it as a shift, it should just shift the previous graph over to the left by 2. But we can confirm that, like see what happens at -1 if I plug a -1 in. That's in 1 over -1, which is 1, 1, like -1, 1. If I put a -3 in, -3 plus 2, it's going to be -1 again. But this time it'll be negative. This was positive. Right, if I put 0 in, I get 1 over 2, so I get the half point there. You can pin it down with a few points that are going to make it more accurate. But again, now what happens with the end behavior? So as x gets really big, so if you throw in 100,000 into x, or even 10,000 will help you out. Even 1,000 will help you out, because 1 over 1,000 plus 2 is not much different than 1 over 1,000, because as you increase, it's just going to get bigger. So as you increase, it gets closer and closer to 0, but does not touch. And again, as you make bigger and bigger negative numbers, it's just going to be coming in from the negative side. But again, it does not cross, it does not touch. And if you think of what possibly could you throw in for x to make that equal 0, which is really when it would cross the graph at 0, what do you plug into that to make it 0? You have 1 over something. How do you make that 0? The only way for a fraction to equal 0 is if the numerator was 0. There's no way to make this fraction equal 0. That's another sort of justification of why it's not ever going to reach 0. So it turns out that any rational statement with a higher degree in the denominator will always approach 0 at the far behaviors. And we'll do a summary of this later, but if the degree q of x having higher degree than p of x, if it has a higher degree, even if it was x over x squared, that's just gonna, like, if you put 1,000 into both of those, you're gonna have 1,000 over 1,000 squared. Like you're always gonna have more, so much more on the bottom that it's gonna approach 0. Especially if it was even higher, it'll approach it quicker, right? You'll have that y equals 0 asymptote. So you'll start noticing that as the examples go on. So y equals 0 is a very common sort of horizontal asymptote, especially when your denominator has a higher degree, so it's stronger. So you've got one, you're dividing a fraction, and the bigger numbers on the bottom, you're going to get close to 0. Right? You can try, like on your calculator, 1,000 divided by 1,000 squared, it's going to be 0.001. So you can imagine as you go on, it's going to get closer to 0. Okay. So far, let's take stock. A vertical asymptote is going to come from what the denominator does not equal, right? And the horizontal or other asymptote is going to be coming from what you see at the really extreme end behavior points. Okay, those are 2 pieces of information so far. Let's keep going with a bit more of an example here. Here's another one. A little small, but okay. So what do you think this looks like? So again, Our denominator is a higher degree than the numerator. So very likely that's going to imply it's going to approach 0 for really big numbers or really small numbers. You can try it. You can go 1 over 1,000 squared and 1 over negative 1,000 squared. Like, what's going to happen? Like, to plug in for x. It's useful to right away go in and factor this. Why would we want to factor this? Right? Because remember, for vertical asymptotes, if you try to identify vertical asymptotes, those come from the domain. So the domain is all real numbers except for what numbers are not in the domain. That's going to help us identify a vertical asymptote. And the horizontal asymptote is something that we need to consider as end behavior. Okay, so I want you to think about that for a little bit and see if you can identify at least one of the asymptotes that this is going to have. So for domain, you could say it's not -2 or -3. So when we write asymptotes, though, you don't want to write just one number. You want to write whether it's x equals or y equals, or like it's basically a line equation that you are writing. So in this case, for vertical asymptotes, when we're looking at the domain, those are x equal statements because those are restrictions on x. You would factor the bottom and you would see what the denominator makes, what would make the denominator 0. And those are the numbers that are going to be your vertical asymptotes. Because those are the places of discontinuity that are not allowed to happen in your table of values. When you do your table of values and you plug in a -2, you're not going to get anything, right? You get no solution, it does not exist. But if you go -2.1, you will get a really big or really small number. So you can always decide where those numbers are going to be by checking around the places of discontinuity. So at -2, you're going to have an asymptote, and at -3, this one, a little tight. So, okay. I mean, you will want to check, like, what happens at -3.1 and -2.9. That'll help you decide, is it like approaching here or is it approaching here? So I will have a positive coming in on this side. You see what I'm doing? You can use a calculator to plug it in. I'm just trying to do it in my head. If I put a -2.9, this will be a positive and this will be still a negative. So this one will be coming in from the negative side. So I can kind of just look around the area and plug points in to see how it's going to approach that if I'm sketching a graph of it. So most likely based on this, well, there's one more thing I need to know before I do all this, and that's, what is the end behavior like? And all of these will have something that the end behavior approaches. It just might not always be 0. But in this case, because you have the x squared in the denominator, and it's 1 over, it's very likely going to be y equals 0. So you can always check. So as x gets really big, what happens? 1 over 1,000 is going to be getting closer and closer to 0. And as x gets really small, again, it gets to be smaller and smaller to 0. So y equals 0 is an asymptote. And once you see the summary, you'll notice that as soon as you see that the denominator has a higher degree than the numerator, you know you're going to have a horizontal asymptote of y equals 0 just because of that fact. Okay, so what that means is that most likely, if I was to sketch this, it'll look something like this. And then probably something, they usually kind of cobweb in. I would have to find more points to be more accurate. And then most likely it will kind of do something like that. And I know that just because I've worked with these so much, I know that they kind of alternate. But if I want to double check, I just plug some points in. So like what happens at -1? Okay, -1 plus 2 is 1, -1 plus 3 is 2, 1 times 2, 1/2. So at 1, it should be like closer to a half. It should actually be tighter in. But, you know, I can like make it more accurate as I find some points. Maybe it's more like, maybe it's tighter of a curve. If you're doing it by hand, just draw like the little arrow pieces first to determine where they are approaching. Well, first you want your asymptotes figured out, because those are defining where it's going to be. And then you want the green, so blue, and then you want green. And then you might want to identify some points, specific points that you found or whatever, right? And then you can kind of blacken the sketch. Like that's kind of how I would go about it. So let me just show you 3 examples. This is going to be the summary. I'm not going to do this yet, but notice that these are almost the same, except for something of the first term of each polynomial and how it relates into the numerator and denominator. So I'm going to use purple for the degree. So the degree of the denominator in the first one is 3, right? Whereas the degree of the numerator is 2. Degree of the denominator here is 2, and the degree of the numerator is 2. So now, like, you can kind of see that in that second one, the degrees are equal. So that means those polynomials are going to be of the same strength. Whereas in the first one, there's going to be a bigger strength because exponents make things more strong. Like if you take 1,000 and you cube it versus just squaring it, it's going to get bigger and bigger quicker, if that makes sense. And then in the bottom one, so these are the 3 cases for your other asymptotes. The bottom one, you have a lower degree and a higher degree on top. So we're going to deal with that as well. So we basically have 3 cases. So first, you want to get vertical asymptotes, and those come from the denominator when denominator equals 0. And that gives you like x equals types of asymptotes. Other asymptotes are going to come based on what happens with the far end behavior. And that's going to have to do with looking at what happens with really big numbers plugged in. And that is going to basically be brought into 3 cases, case A, case B, and case C. And those cases are going to be categorized based on the degrees. We'll get there though. We're on case A right now. We're on bottom is of a higher degree. So we're going to explore the other 2 for the rest of today. Let's take a look at this one. Again, this is higher degree in the denominator, but I want you to see something in this one. So maybe just take a minute. Let's just think about this and see if you can identify any asymptotes directly here. So you want to factor it, and then you'd want to write it as line equations. Yeah. So let's just take this and factor it, because factoring it is always going to be really helpful, regardless of what we do here or what it looks like. Oh, does anyone notice anything? So yeah, like technically right away, what I can say is that in my domain, I have all real numbers except for -2 and -3. Does anyone notice anything though in this example? I've chosen it very carefully. Yes, we can cancel it out. So careful here. So once you factor it, and if something cancels out, this is going to change the entire shape of the graph, except for the fact that the domain must remain the same. So even though this x plus 3 cancels out, because the original equation is this one that we're graphing, we still cannot have x equal to -3 at any point. But what this means is that when it cancels out, it will look like the graph of this, which we've already graphed, and we know looks like this, approximately. I totally sketched it. But we've already done that graph, right? Earlier, it only has just those two asymptotes, not the -3. But what this means is that because we still could not have anything at -3, whatever -3 was, that point there becomes what's called a hole. So you have to just draw a circle there to indicate that there's nothing there, but everything else approaching it is still there. So this is if something cancels out. Just keep in mind the domain is still not including that number, but instead of an asymptote, it will be a hole. Okay, so I mean, you can try this one out right away just to sort of speed up the process of what you would look for. This is x minus 2, x plus 2, and it's 1 over that. And so vertical asymptotes, as you may expect, would be x equal 2 and x equal -2. And because when we put really big numbers in, we get close to 0, our horizontal asymptotes are going to be y equals 0. And so we can quickly sketch it. And now I just have to find some points. So it'll probably be like that. And then, you know, you could plug in what happens at like -4 and what happens at 4. And I'm pretty sure these usually go like opposite, but again, maybe plug in some numbers and check. But let's go to some ones where it's different. So let's just take a look at this one. What could we plug into f of x? So for x, so that the whole fraction equals 0, which means the only way that happens is if the numerator equals 0, right? I'm curious, when is it equal to 0? Which actually just means when is x plus 1 equal to 0? Yes, at x equal -1, I have a point. -1 gives me 0. So this is a little bit, this is the point where even though the horizontal asymptote approaches 0 for the really big numbers, there is a point at which it is crossing that 0 line. And that is okay, because end behavior is different than just central kind of behavior. So -1, 0 is a point. So very likely, and we would have to maybe plug some more numbers in. I'm kind of thinking it might look like this. But that is just my guess. I want to double check and draw those little arrows by each of those asymptotes first. So let's double check a few here. And again, you could put this into your graphing calculator for y1, and you could make sure you include bracket divided by bracket. And then you can use the table and you can just, I mean, you can graph it. You can also just identify points that way. You know, you can check at 2, what happens at 2, positive, positive, positive. So it's probably going to look like this. Plug some more points in to check, and probably going to look like that. Okay. So what I really want to emphasize with this example is even though, so these ones cannot be crossed because they're a domain issue, right? You can't have anything equaling that. But this is really just like an end behavior guideline. So if you have an x in your numerator, you can also solve the numerator to 0, and the numerator to 0 gives you the x-intercepts. You can also find y-intercepts, obviously, by plugging it in and checking that as well. Okay. Okay, so let's just take a look at what happens now with a different degree. So we have two options. One option is, let's go to this one here. One option is denominator is bigger, and we just looked at that. When the denominator is bigger, it's growing at a faster rate, so you're always going to have y equals 0 as your asymptote. Like, you could check it as many times as you like, but it's always going to approach 0. It doesn't really matter what these numbers are, what these numbers are. Because of those degrees, that's what makes the difference. So we've seen that in many examples. We don't have to dig that in anymore. And again, whatever makes the denominator 0 is obviously going to be your vertical asymptote. Whatever makes the numerator 0 is going to lead to your x-intercepts. That leaves us with the last two cases. So what if the degrees are equal? So I want you to take your calculator and say you have 1,000, you're plugging in 1,000, but we're not going to do it for everything because we can kind of imagine that because x squared is so much stronger than x, I'm just going to go, so as x gets really large, so I'm going to just try x equals 1,000 maybe. What happens then? Well, I'm going to have 6 times 1,000 squared plus a bunch of stuff over 6 times or 2 times 1,000 squared and so on. So what's that going to simplify to approximately? Like, just try it out. So, you know, you could even do 100 or 10 squared. Like, you know, what do you think is going to happen if you go 6 times a big number times itself? So that's 6 million, and then divided by 2 million. And plus or minus some things, these are going to be small things. So what do you think this is going to approach? 6 times something of a similar size as 2 times that something. 6 over 2 is 3. It's going to get closer and closer to 3. You can try it. You can plug in into a table of values. Maybe just try 10. Maybe 10 is easier for you to convince you. So let's say we put in 10. So plug a 10 in for all of this stuff. 6 times 10 squared, so 600 plus 30 plus 5 is 635. If I'm putting x equals 10 in. And 200 minus 20 plus 1. Hopefully everyone sees what I'm doing. I'm just plugging in a 10 in and seeing what that's going to give me. 635 divided by 181 is about 3.5. Now, if I increase that number higher and higher, if I make it a 20, if I make it a 30, if I make 1,000, it's going to get closer and closer to 3 because the leading coefficients of those equal powers simplify to 3. 6 over 2 is 3. So your asymptote is going to be y equals 3. So let's try another example, and we'll do it on Desmos so we don't have to sketch everything about it, because everything else is going to be the same, except for the fact that instead of having a asymptote at y equals 0, you're going to have an asymptote at the ratio there. So I don't really, at this point, I don't even know if these factor really nicely, but what I do know is that we have an asymptote at the two places where the denominator is going to equal 0, whatever the denominator factored to. It could have been a quadratic formula necessary, but 5 over 10, so y equals, and what's 5 over 10? It's 1/2, right? So you can see that it gets closer and closer to 1/2. The green line is 1/2. So that is where the asymptote is for our horizontal one. So let's try. So take a look at this one. It's got equal powers, equal degrees. Can someone tell me what they think the horizontal asymptote is going to be? Now that you've learned about this like leading coefficient thing, what's the horizontal asymptote going to be? Y equals what? 2, yeah. Because 2 over 1 is the leading coefficient. That's what that simplifies to. If I had a different function and it had a 3x to the 4 plus a bunch of stuff over a 4x to the 4 plus a bunch of stuff, my asymptote would be 3/4. Because I don't really care, because all of that, as it gets really big, is going to just simplify out and it's going to get closer and closer to 3/4. Not equal to 3/4, but closer and closer to it. So we have that. We want to factor it to check what our other asymptotes are. And we want to consider if the numerator is 0, that's where you're going to have your x-intercepts. So if that's a bigger thing, you want to factor that, identify your x-intercepts. When your denominator is 0, that's going to give you your x-asymptotes, right? Vertical asymptotes. So for this one, it's going to be 0, 0 is going to be a point. Y equals 2 is going to be a horizontal asymptote. And x equals 2, x equals -2 are going to be the other asymptotes. So most likely we're going to have this sort of thing. But again, like find some more points and make it a little more precise than I am. So far we've done the first two. Denominator is a bigger power, get y equals 0. If they're the same powers or degrees, it's going to go to the leading coefficients. So in general, like if you had a and b, it would go to y equals a over b for the same power. And there's a formal definition, but it essentially says this, like if n equals m, then your asymptote is going to be y equals a over b. So that leaves us with the last one. This one's possibly the most complicated, but also the one that shows up the least. And that's the one where if you have a x to the n and b x to the m, where n is greater than m. See, in this one, n was smaller than m, right? The bottom was bigger. I find this notation just confuses people. So basically, if the top has higher degree, then what happens is we have this sort of polarization to whatever the top is, and it's actually going to leave us with something that's called a slant asymptote, not going to be horizontal. Although this vertical is always going to stay the same, like you're always going to look at the denominator vertical. So let's just look at a simple example in Desmos of that and what that looks like before we do like a more formal one. So let's say we had x to the cube divided by x plus 3. I'm just going to make that a square. Okay, so see how instead of a horizontal asymptote, you have a slant line asymptote. And that's because if you go x squared divided by x plus 3, what ends up happening is what would happen in a division. I'm just going to write this as we have that, and we're dividing it by x plus 3. Whatever is left after that division means that the numerator was stronger, and it's basically going to whatever the quotient was of that division. I know this is a little bit tricky to see, but let's run through it and see if it actually shows us this line when we do this. So when you do the long division, you're like, okay, 1 times x plus 3. You could, I guess, do synthetic in this case, but sometimes it's a little harder then. And then you would go minus 3 times that. So what does that mean? So f of x is x squared over x plus 3. But that equals the quotient x minus 3 plus the remainder that has not yet been divided by that. So now when you think as x gets really big, the y, or the f of x, is approaching x minus 3. Because as this gets really big, this actually 9 over infinity is going to start getting really small to 0. And you're going to be left with the quotient. That's how you get a slant asymptote. And if you look at this, y equals x minus 3, because that's 50. So that's what this line is y equals x minus 3. You're only going to get examples where these degrees are off by 1, because when you do a cubic divided by degree 1, you're going to get a square, like a curvy asymptote, which we're not doing in this course. We're only doing plain, simple linear asymptotes. So let's just see if we can fit in one more example of that. So here's one. You have a higher degree in the numerator than in the denominator, so you can't assume it's going to approach anything until you long divide. Whereas here, right away, I know my asymptotes are, first of all, whatever it is from my factoring, and then I also know it's going to be y is approaching 0 for that. But because in this one, we've got a higher degree, I'm going to have to long divide. And whatever's left here is going to be what my asymptote is going to be. I'm still going to have the other asymptote from here, x equals 4. I can still identify if this equals to 0, then those will be x-intercepts. All of the same stuff exists. It's just instead of the horizontal asymptote, I have to long divide to get the slant asymptote. So let's see here. Yeah. I don't really care about what the remainder is. I care that my slant asymptote is going to be this. So when I graph it for this one, I know that I'm going to have at x equals 4, and I know that I'm going to have at 2x plus 8, and I might have to make my graph bigger. Whenever this numerator is 0, I might have, say, 2 points that it crosses, and maybe it ends up looking kind of like that. So that is an example of when you have more sort of power on top there. That doesn't cancel out. Like you can see this one here. When I factor it, this cancels out, so it reduces, and this will have a hole, and it's just going to be whatever y equals x minus 4. It'll be a line with a hole. But if it doesn't cancel out, then we get that slant asymptote there. Those are your 3 cases. So to recap, factor everything. Look at when the numerator is 0. That's going to give you your x-intercepts. When the denominator is 0, is going to give you vertical asymptotes that it never crosses. And then for the other asymptotes, you have 3 options depending on the relationship between the powers of the degrees of the polynomial. It'll either be y equals 0, y equals the leading coefficients, or a slant where you divide the numerator by the denominator.